around a little bit, go back and forward in time and have a few little segues. It's not going to be death by PowerPoint. It's I've got some kind of fun stuff in here, and so to kind of get started, the history of radio is obviously a really broad topic, and in order to do any kind of a presentation in just an hour on the history of radio, there needs to be a focus to it. It needs to have some sort of a direction that we're going to take. And so I gave this one a lot of thought how we would present here at the LeMay in talking with Dick and with Stacy and just kind of thinking through what we're going to do here. What I decided to do, since you have a collection of radios and you go see the radios and they've got placards on them that say what they are and when they are, I was thinking that maybe it would be more interesting for people who have an interest in radio to maybe dispel a lot of what you think about the history of radio and where it really did come from. Most people, you say, where did radio come from? Oh, well, it was invented by Marconi. And there's a lot more to the story than that. So what this presentation is going to be, we're going to start around 1820 and go into the 1920s, because it took that whole 100-year period of time for all of the concepts that we know as radio to come about. It didn't just happen one day, like a lot of other things in invention. So that's the kind of the focus of it. So I thought it would be interesting to go back and meet some of the people and just show you some of the things that each one of these persons contributed individually to the development of radio over that 100-year period. So first up, we're going back to the 1820s with a guy named Hans Oersted in Denmark. He was one of the very first physicists to ever study magnetic fields. And I chose to start with him rather than going back to volta for the volt, or going back into really early periods. Once magnetic fields started to get studied, that's when all the moments started happening, because some interesting things started coming out of those studies. Oersted demonstrated principles and effects with magnetism that would become integrated into virtually all the aspects of electricity, electronics, and one day, long after his death, radio itself. He laid the foundation of magnetic fields and knew that there was something more to them. It wasn't just a magnet that can pick up a piece of metal. There was more to magnets than what we thought. And to this day, he had a unit of measure named after him called the Oersted. It's still used by engineers every day for the study of magnetic fields. We use that abbreviation. The next person in our list is a name that most people will know, and it's André-Marie Ampère from France in the late 1820s. And he's the guy that founded the science of classical electromagnetism, taking the work of Oersted and demonstrating that electricity and magnetism are actually very related to each other. And he started building a very solid science around electromagnetism for the first time. And of course, radio is an electromagnetic medium. So again, that's why we're back in this time period, because these are the core technologies that have to be present for radio to ever occur. And of course, if you've ever said that you're all amped up about something, well, you're using the unit of measure that is named for Mr. Ampere, which of course is the amp, which I think most people certainly know that unit of measure. Then we move to the U.S. in the 1830s with Joseph Henry. Now, Henry was more of a practical science inventor kind of a guy. He was all about taking gizmos that had been created or coming up with new gizmos that he invented himself and improving them. And he had a knack for fiddling with all things electromagnetic. So he was the guy that gave us the very first electromagnetic devices, like an electromagnet or a relay, which is a form of electromagnet that's used was used in the development of telegraphy. And so because of the work of Joseph Henry, that's what gave us telegraph sounders. And of course, once we have telegraph, now more of those moments where people start thinking about, wouldn't it be neat if we didn't have to have those blasted wires running from point A to point B make it work. But the system was there, and Samuel Morse was, you know, and others, well, not just Morse, had developed, you know, the Morse code that could be used to communicate over wires, and people started just having those thoughts about maybe we can go beyond this. And just like Ampere and Oersted, he had a unit of measure that we still use today, and as a radio guy myself, I very much get involved with the unit of measure called Henry, because I work with transmitters and receivers, and the coils, the inductive devices inside transmitters and receivers, we have to keep track of how many millihenries or microhenries of inductance are in those coils, and that's the unit of measure that we're actually measuring with a Henry, is inductance. And of course, in the real world, a Henry, a coil that's a Henry would probably fill this room. It's a gigantic amount of inductance. So we deal in thousands and millions of a Henry. In some cases, even billions. In cell phones, there's picohenry coils. So it's a very, very important unit of measure. Now we're starting to get into the really fun guys, the people that did some pretty amazing things. And Michael Faraday is certainly stands out among a lot of the early physicists, developers, engineers, and electronic tinkering dreamers. He was a lot like Tesla in a lot of ways, which we'll cover as well. He furthered the sciences that were leading to radio. He kind of took in on what a lot of other people were doing and really made some improvements in a practical way of making these technologies practical. So he's the guy that gave us the first real practical electrical motors, which would become integral in early spark transmitters. You can't have a spark transmitter without an electrical motor. And so Faraday fed into that electromechanical way of thinking. And you know, he also figured out that a motor can also be a generator, and early dynamos, as they were called, different kind of generator than we use today typically. But he did a lot of developments in that technology as well. And again, this all relates to early transmitting gear because it all involved dynamos and electric motors. And of course, his namesake device. Can anybody name what is Faraday's big famous thing?
Faraday cage. Faraday cage?
Faraday cage. That's his big claim to fame. This is an actual photograph of somebody using a very large Van de Graaff static generator, producing somewhere in the neighborhood of a few million volts, striking a person who is inside a Faraday cage. And a Faraday cage is just a bonded metal cage. It can be screen or cage, any kind of metal, all bonded together and grounded. And it doesn't matter how many volts you hit it with, they can't go in there. That's like your little safe space. And they're used all over the world in military facilities, and people even have them in their houses for protection from EMP, electromagnetic pulse, which, you know, is a horrific terrorist tactic that has been predicted to occur at some time in the United States, most likely, where a bomb is detonated a mile high. It's too high to actually destroy anything, but it wipes out the entire electrical grid. And anything that's electronic, whether it's turned on or not, if it's solid state, is destroyed. So Faraday cages, or as they're called now, here's another great shot of a couple of girls up in a hanging cage. This was from a stage performance showing these brave girls being zapped in this cage, and she's a little hard to see probably, but she's got her hand right up to the middle on the cage while she's being zapped. But it has led to commercial developments for the work of Faraday. We have big Faraday shields, Faraday cages that go into military bases, around computer facilities. This is a commercial unit that's marketed, and this is what it looks like when it's being built. Just a metal framework that's then filled in with metal panels, and the whole thing is grounded to create a big Faraday shield. So Michael Faraday did a lot of work with electromagnetism and with spark energy, with the effects in generating high potentials, and his work with motors that would lead to spark transmitters. So he was very much at the forefront of that sort of stuff. And the Faraday cage concept has gotten so popular, especially with some of the prepper movement, that you know, they make them for homes now. This is one you can buy and install in your living room and then sheetrock over it, and, you know, make it be your kid's bedroom. And it even goes to the absurd point, I kid you not, Faraday cage underwear. That's a real ad. I found this on a fluke. It's an actual advertisement from the Telegraph newspaper in London. Yours for the low everyday price is $65, and you can protect your package from radiation. It says it right there. What would Michael Faraday think? I think he would leave the room. So next up, we have another fascinating person, James Maxwell from Scotland in the 1860s. This is the guy that really brought us truly the first glimpse of what radio was. Now, Maxwell didn't build things. He didn't even build apparatus. He was completely a theoretical physicist. But he was the first one to actually predict that electromagnetic waves, radio waves, would travel through the air just like light and at the same speed as light. That was monumental. That probably, when he made those announcements and white papers and whatnot, probably came across as almost like witchcraft at the time. That had to have been a monumental thing, something you can't even see traveling at the speed of light. But he did a lot more than that. Much of his research actually paved the way for Einstein. Einstein actually considered him to be one of the greatest mathematical minds in history, Maxwell. And a lot of the work that Maxwell had done about things moving at the speed of light cut years off the time that Einstein would have had to spend doing it. He was able to take Maxwell's work and incorporate it. And his legacy goes really, really far beyond what he was doing back then. His mathematical and theoretical predictions resulted in us developing a kind of radar called cloud-penetrating radar or earth-penetrating radar. Not normal radar, it's a little bit different way it has to work. And some of the theoretical accomplishments Maxwell did actually led to this little blob of a photograph here. This was taken in 1960, and it's the first photograph using cloud-penetrating radar of the first mountain range ever seen not on planet Earth or the moon. It's actually on Venus, and because his mathematical formulas were used in a practical way to develop cloud-penetrating radar back in 1960, they named it the Maxwell Months in honor of him, because that's what led to that development. And here's a more modern picture taken by satellite of the Maxwell Months. So some of these people that were bringing these amazing technologies, they're still very much around today, and their principles and concepts being used that all contributed to the development of radio. Oops. Oh yeah, here we go. And like so many others, he also has a unit of measure that's still very much used today called the Maxwell MX. That is what is it, magnetic flux measurement. It's still used today. So now we're really getting into the nitty-gritty of words, people's names that become words we know on radio, and this is probably the first really big one, and that's Heinrich Hertz from Germany in 1887. He is the first researcher, physicist, tinkerer to systematically and unequivocally create an intentional transmission of what we call radio waves. It wasn't an accident, it wasn't an experiment, it was, he theorized that this would work and he built a device to do it, and it did what he thought it would do. That was a landmark moment because he created radio waves. His apparatus was very simple, very elegant, and those that understand anything about a schematic will get this right away, but it's a very simple idea. There's a step-up transformer where we have a primary coil on a transformer and a secondary coil on the transformer that produces a much higher voltage, and that voltage then jumps across two electrodes, and then there's big metal balls is what he used, but they later become big metal plates and ultimately would go out to antenna wires that would radiate that signal. And in Heinrich Hertz's first transmitter, the electromagnetic energy that we didn't know was called radio then, we didn't use that term, actually passed through the air in a way that he didn't really understand. He wasn't a theoretical guy, but he knew that if he put a ring of brass, I believe he used, with two balls with a much closer gap at the end of them, that every time that he keyed the key up here and made that spark happen, a little spark happened over on his gap over here. And that demonstrated that those waves, that energy predicted by Maxwell, in fact did jump through space to those other points, and it manifests itself there. And here's an actual practical adaptation of that. So here's the spark gap, and here's the little balls on the end radiating the signal. We have our Morse code key, and here's our step-up transformer. But ironically, he just dismissed the whole thing as interesting, but he said it will never have any practical purpose, which always reminds me of the head of IBM in 1954 saying that the world will only ever need 4 computers. I think I'm running about 6 of them up here right now. So sometimes these really brilliant people they don't see beyond the immediate, and that takes other people to take what they've done and go with it. But what he discovered and demonstrated, and he kind of built the science of, are what were called at the time Hertzian waves. Again, he didn't really understand them or how they worked. That would be later people that would figure that out. But we now call it radio waves. And in 1960, in honor of that, the scientific community, for the most part, agreed to change cycles per second to, I need my reading glasses for the next slide, to the term hertz, which of course we all use today. And I say, by and large, there's some parts of the scientific community that, for whatever reason, rejected that and refused to use other than cycles per second. Not sure why they do that. But by changing it to hertz, then we get all the wonderful Hertzian derived frequencies, the biggest being, of course, kilohertz, megahertz, and gigahertz. And even with my reading glasses, what I see is what you see.
Focus.
It's a little out of focus, I think, but let me see if I can fix that a little bit. Keystone. I think we had it dialed in advance, about as good as it's going to get. So we ended up with a long legacy of hertz, and that so obviously directly ties into radio, because we talk about megahertz all the time. So hertz was very pivotal in the development. But next, now we get to the people that are hero status, and a lot of people, when you mention Marconi, oh, he invented radio. And you can probably see by now that he didn't. What Marconi did for radio is what Henry Ford did for the automobile. Marconi, through his entire life, was he was aggressive, personable. He had visions and dreams, and he knew how to go out and accomplish them. And that's exactly what Henry Ford was. Henry Ford didn't invent the automobile, he just made a better way to build it, and he made it incredibly popular. And Marconi did much the same, not so much a better way to build it, but he said, okay, I get it. I know what this can be used for. So he picked up where Hertz left off and said, oh, okay, I'm going to make this work. You're on something really good here, pal. And he created a development of radio that went way beyond Hertz. So in 1901, they hoisted a 500-foot wire from a kite in Newfoundland. And by the way, they picked Newfoundland because it's the closest land area to someplace in England where they'd be able to set up to receive. Because if you look at a map of where Newfoundland is, which you'll see here in a minute, it's the closest gap to get a signal across the ocean to Europe. And while there was no press there during the actual test and transmission, by popular demand after he succeeded, he reset the entire setup. So this is a recreation of what it looked like, but taken just a few weeks after his monumental success. And this is a little video I'm going to play where you can actually hear a Marconi-built spark transmitter. This was actually built by and owned by Marconi. It's in a museum in Newfoundland near where he did his transatlantic contact, and it's not a particularly powerful transmitter. This is the same transmitter that was aboard the Titanic and the Olympic. By today's standards, it would be like the basic transceiver I use at home, a Yaesu FT950 100-watt transceiver, which for those that aren't familiar with that sort of stuff, it's just your standard ham radio. I don't have a big amplifier. I'm not like a big gun, as we call it, ham radio. It's just a decent basic transmitter, and I can talk around the world with it, but I'm not a powerhouse. That's what this was. This wasn't a hugely powerful transmitter by any stretch. But this little video here, hopefully we'll be able to hear okay on the projector, but it's just like a minute and a half long, so we'll let this play while I get a drink of water.
This is a Marconi Spark Gap transmitter from the early days of radio. And the way that this works essentially is that it's a big step-up transformer, and the telegraph key is a switch that turns it on and off. So when you close the contact with the telegraph key, a spark jumps across the gap between these two electrodes over here, like this. And this would also be hooked up to an antenna, so that would be spewing out radio waves across a broad spectrum of the radio frequency. The problem with these is that when one was going, the sort of strongest, loudest one was the one that could be heard, and you had trouble hearing all the rest of them.
My apologies,
Such a scramble to set up, I forgot to plug in the laptop.
You got one power, right?
Right here.
I know, but I don't know where I put the laptop power supply. Oh, no. Well, thank you for coming, everybody. No, if all else failed, found it. Nope, that's the other laptop power supply.
You really do have 6 computers.
I know I took it out. It's not bad. Oh, wait.